generic application process. I need to stop Power iLock because I'm about to change, to bring up and change some of the specifications here. I use for this Cygwin, which is a Linux-like environment in Windows, but you can use any way of handling files you like. Okay, I have my packages here. Demo design port of 0. So let me show you something. If I open the implementation of the switch logic, and I like Emacs, you can use any tool for editing files, but here I will use Emacs. If we look at, and this is part of the answer also to the question I got previously, what is the package? Well, with a package, you have a number of files that define signaling principles. So here for this demo principles about the switch is a condition for when to throw the switch to the left and when to throw it to the right. You can see here that there are 5 conditions that need to be fulfilled for throwing a switch to the left. The first one is that it's not locked. This is a not sign. The switch must not be locked, and the switch must not already be placed to the left. Then there's no point of throwing it to the left. The switch must not have a write request, so a request to be thrown to the right by the human machine interface of the Office system. And it must not have a request to be thrown to the right by some root. So when you request a root, the switch moves, as I showed before, and there must not be anyone that wants to switch to the right. And so these are 4 negative conditions, and then there's a final positive condition that either you get a request to throw it to the left from the Office system, or a root needs it to the left. So pretend now that we have a little error here. We introduce a typical error. So instead of saying left, we say right. You're a bit confused when you write this, so you put in the right instead of left. Let me now open this little project I have. I need to open it like this. Here we have it. If I open it up now, it will load again all these packages. As I said, it takes a bit of time because it checks first that there are no changes in any of the packages, and there are quite some packages with quite a lot of files in them. So this little check takes some time. And actually, it will probably show us a little change now because I changed this file. Yes, it says integrity checked failed. There is a new automatically saved file in here, but there is also modification in this one. Okay, so, but I ignore that now because it's for demonstration purposes, and let me start this one. So, for example, this one, this is a switch here. The logic for throwing it to the left has been changed, so it will not work anymore if I request a root like this. It will not throw the switch. But I didn't change the possibility to throw the switch by a manual request from the human machine interface. So we can try this one. And also see what this, how we can discover such errors using simulation and formal verification. Okay, let's open up the simulator. Here now, if I request this root, you see that the switch here doesn't throw anymore, and the root remains requested, it doesn't lock. But if I send this left request HMI, the switch will throw and the root will lock. For roots with I only changed the condition for throwing left, so no roots to the right will be affected by this. Let me take away this root, releasing it. If I run scripted tests, you will also see here that some tests are now red. if you look at some tests, you see that most of them work, but 2 of them don't. And it's because 2 of these routes require switches to be thrown to the left. This one and the other one is the exit route here. So you see S1 to S4 is from signal 1 to signal 4 here. And the other one is S3 to exit, so from here and out. So here is a very convenient way of discovering strange errors in the generic application as well as in the configuration data. If we run formal verification, however, this will not, everything will still pass. It's all green because the error we introduced here was not really safety critical. It just prevents some routes from being locked. So you don't get any safety hazards with this. So I want to show you also some other example where you actually introduce something unsafe. Let me revert this left. And then let's look at the locking conditions up here instead. For locking, this is an OR symbol. So for locking, we say that there are 4 different reasons to lock. The first here says that the switch's track, this track circuit on the switch's track is not vacant. That's a reason to lock. So if you occupy a switch, you are not allowed to throw it. The second one says that if there is a track circuit path, so a path of the track circuit that locks the switch, then the switch should be locked. And then there's flank protection reasons and front protection reasons to lock the switch. I'm not going into details because this webinar is not really about the signaling principles, it's about the tools and processes. So just imagine that we forget in the design one of these things. We forget the occupancy here. And I open up again this project. So / means a comment. So in effect, I remove this line. I comment it out. So I'm opening up again and validating all the files. Okay, here it says the same. This file is still changed compared to the checksum. And now, if we run simulation, I'm pretty sure that all the safety requirements, all the test cases will pass now. Everything will be green. So we'll not find this error using tests because there is simply no test for this particular case. But we will see that we can show it using formal verification. Let's go back here. You can see all the tests have passed. But if you run formal verification, I'm pretty sure we will prove that some requirements are not fulfilled. Yes, we look here. Both switches, they violate this requirement. A non-vacant switch must not alter its position. So if you want to look more at this, you can double-click this failing, and it will create a scenario for you when the switch actually alters its position, although it's not vacant. So you can see here, it's ladder logic, and this means that vacancy is not on, so it's not vacant. And you can see that -1 means previous step. So it says that if it was, sorry, I need to think of it here. It's about throwing to the right. It says that now it's put to the right, but it was previously not put to the right. So something has changed here, although this was not vacant. And if you click here and see why, you can see here that it checks this throw right and locked. And here you can see that there is no check anymore for vacancy. So actually here you can view all the equations in the design using ladder logic, which many signaling engineers find very convenient. You can see with the blue here means that the metaphor is that it's like a closed part of the circuit, Red square means that it's a broken part of the circuit, an open part, and moreover, it might be the explanation to why this why the whole circuit is not closed.